Hello everyone, I'm Mert, currently a PhD student at Texas Tech University. In this talk, I will introduce our paper, LockedDown, Exploiting Contention on Host GPU PCIe Bus for Fun and Profit.
Modern GPUs have become increasingly popular over the past decade. On the one hand, they are needed to perform resource-intensive visual computing tasks, such as graphics rendering. On the other hand, along with the development of general-purpose GPU programming models like CUDA, modern GPUs have also been extensively used for performing massively parallel computing tasks. With this work, we discovered that the contention on the interconnect between a GPU and its host system introduces a side channel vulnerability that we use to mount a covert communication channel and a website fingerprinting attack. Our side channel shows that the host GPU PCIe bus is shared among processes running in different security domains, such as virtual machines, and the contention on the PCIe bus is measurable as a data transfer latency. We leverage the measurable contention on this bus to leak information across strong isolation boundaries. Before we dive into our methodology, I would like to give some quick background on typical PCIe topology. PCIe is the de facto interface to many high-speed peripherals, including GPUs. In general, the first one or two PCIe slots on a motherboard are connected to the GPU via dedicated PCIe lanes. Any additional slots on a given motherboard need to go through PCIe switches, commonly located in the platform control hub, which has rather limited bandwidth. This allows GPUs to have a quick and less interrupted pathway for memory transfers. Traditionally, the host GPU data transfers are handled via a DMA on the PCIe bus. To avoid being potentially disrupted by virtual memory management operations like swapping, DMA requires that the memory pages corresponding to the DMA buffer be locked in the host memory, which means that the physical locations of the buffer are immune to any paging activities. Under the circumstances where we need to transfer a piece of data residing in regular host memory pages to GPU memory, the CUDA runtime first copies the data into a page-locked memory buffer that is temporarily allocated, and then uses the DMA to transfer the data from this buffer to GPU memory. This two-step process is illustrated in this figure. However, the extra copy adds delays, which greatly reduces the achievable bandwidth consumption. CUDA also has a feature that allows users to request the allocation of page-locked memory directly. If the data to be transferred is already in such page-locked memory, the CUDA runtime will not involve any extra memory buffer, but instead just uses the DMA to copy the data from the host to GPU. This knowledge allowed us to work on introducing heavy congestion on the host GPU PCIe bus. We have investigated 4 different scenarios under different memory transfer types and sizes to find the optimal scenario for this side channel. We saw consistent increases in the host to GPU data transfer time if the host data resides in page-locked memory. Now that we got the background and the methodology out of the way, we can discuss our covert channel. We have a standard covert channel attack threat model where colluding parties, a sender and a receiver, are on the same physical platform but in different security domains, and the sender has some sensitive data to transmit to the receiver. NVIDIA implements and offers mediated pass-through GPU virtualization techniques under their virtual GPU architecture to provide isolation between different users on different virtual machines. Virtualized GPUs leverage only temporal isolation to share the GPU hardware resources among the vGPUs, except for the GPU memory, which is spatially partitioned. There is a scheduler that assigns each vGPU a time slice, and in the assigned time slice, the vGPU have exclusive access to many of the GPU resources, like the codec engines. There are also certain resources that can only be used by vGPUs without temporal isolation, and one example is the copy engines for the data transfers. We leverage this to communicate between VMs. By using a sender that regulates contention on the bus, we can leak information that the other VMs can observe. A receiver can read this information by measuring the changes in the available PCIe bandwidth. This figure gives an example of how some measured data transfer latencies correspond to sending 16 bits. As for our evaluations, we have used two different platforms equipped with GPUs. We show that our covert channel reached speeds of 90 kilobits per second with considerably low error rates after little optimization. Not only that, but our covert channel is also more resilient against noise than state-of-the-art GPU covert channels. Table 2 shows our naive results without any synchronization or advanced communication protocol. Table 3, Scenario 1, shows synchronization. Scenario 2 shows an optimized communication protocol by dividing a message into fixed size chunks and sending them individually. Scenario 3 shows an extreme case under excessive noise of an HPC benchmark with synchronization. Please see our paper for all of our evaluation scenarios in more detail. Let's switch gears to talk about our second case study, the website fingerprinting attack. As online presence plays a more critical role in modern society, one way to extract intelligence is to monitor a victim's web browsing activities. For this attack, we assume that the attacker has placed a piece of malware on the victim's computer through methods like phishing or physical access. And we focus on a closed-world scenario in which attacker strives to pinpoint the websites browsed by the victim from a known set of possibilities. We observe that when visiting different websites, the patterns of the induced traffic on the host GPU PCIe bus is different. We capture these patterns to use them for identifying which websites are being browsed. From the figure, we see that each website gives rise to a distinctive pattern, which is interpreted as its fingerprint. For our evaluations, we have created a list of 100 popular websites. We evaluated against popular browsers like Chrome and Firefox on both Windows and Linux. Under each setup, we trained an FCN model where the training dataset consists of 100 captured data transfer latency traces for each website. We also collect another 150 traces per website for our test dataset. Our results show that this fingerprinting method can achieve up to 95% accuracy. Moreover, our attack is also evaluated against Tor browser with up to 90% accuracy. This table shows models tested against traces collected under different settings. While most of the results show that cross-setting prediction is similar to random guessing, some entries that are highlighted in the table interestingly show the opposite. As for the countermeasures for our attacks, we propose three approaches. The most naive approach to thwarting our attacks is to remove the page-locked memory allocation and transfer feature from CUDA. However, data transfers from regular pageable memory can introduce considerable overhead and display irregularities in latency. Therefore, this countermeasure presents downsides for many parallel computing programs that require large amounts of asynchronous data transfers. To specifically mitigate our covert channel from being a danger for cloud users using virtual GPUs, NVIDIA can implement a time division multiple access method that divides hardware resource usage into time-sharing slices. If the PCIe is shared via TDMA across multiple vGPUs, then the intermission between succeeding data transfers would not depend on the size of data transfers. Thirdly, a mechanism to detect our attacks can be employed as a countermeasure. Our side channel relies on repeated data transfers to detect contention. These transfers themselves cause a noticeable contention that might be detected by a third party that occasionally measures the transfer bandwidth.
To summarize this work, we show that the side channels caused by contention on the PCIe bus are often overlooked by manufacturers and showcase two attacks exploiting the contention on the host GPU PCIe bus. To the best of our knowledge, This is the first work that explores covert channel attacks under the circumstances of virtualized GPUs. Thanks for listening.